going to try to record a session, and we'll see how that goes. Generally, it's been successful in the past years. If not, I'm just going to hopefully cover the same stuff and give you last year's recording. So this is lecture, well, essentially lab 2. It's more of a lab than a lecture. And we're going to try to learn the elements of a language today, right, before we go into the very heavy stuff, which is data formats, right, which is one thing where C is very good at. So I'm going to show you how to write simple functions with a little bit of, the typical constructs, if, while loops, for loops, and so on. And we're going to also check our algorithmic abilities in the process, and I want to essentially find out from you how comfortable you are with everything you see, right? So you're supposed to have some programming experience, and you're supposed to be able to understand the logic of basic programs. But if at any point you feel I'm going too fast or doing stuff that it's difficult to follow, let me know. Okay, so apart from hello, yes, please. The front.
Can we switch up the front lights? Yeah,
so there's no button. I think it was designed so that it would face that way. So you see, I can turn it either on one side or the other. I can't turn it right. So if you would be facing this way, I could turn the front lights. And I think in most of the classes I had today, as I would enter the door, the screen would be right there, but not here. So what do you prefer? Do you prefer at least half of it? You like it this way? Is that better? That's a first for me. All right, so apart from Hello World, what's one of the first programs we typically write? Yes, very good, Fibonacci. So we're going to write a function that computes Fibonacci, and it's going to be recursive, right? So hopefully you remember what that is. So in C, we're going to see very soon that we need the so-called function prototypes. These function prototypes are generally shared between multiple files, right? Even though we're not going to experience that, or maybe we might, but just very briefly. In general, that's what happens. So these function prototypes are extracted in separate files. This file, stdio.h, and it's not studio.h, as some might be tempted to misspell it. It's stdio standing for standard input output, right? It's a file, and then what we're doing with this directive, everything that is starting with a hash is called a directive, right? What we're doing with this directive is to include that file. It's as if it were typed in, right? And this essentially saves some work, because we can have one file. This set of prototypes, we're going to see very soon what they are, right? These prototypes are shared between files, so we write them once, we include them everywhere, and then it simplifies work. It's as if they were typed in, right? And we'll see later that we're going to write our own H files, all right? They can be opened, if I can find them. I'll try to find them later, and at some point I'm going to show you to you. They're generally very large. And where do these prototypes, they're prototypes of something, and those somethings, where do you think they reside? They reside in the runtime that is automatically brought in by the compiler, right? We're going to see that we need to write prototypes for different reasons, and we're going to have that experience. But you don't have to be worried about that. What's important is that we're going to be using library functions, which are names that are not defined within this file. They have to be defined somewhere. Those definitions are essentially here. That's why we're including this file. This will not be the only header file, and this H stands for header. We call them header files. This will not be the only header file that we'll be using, but it will be most common. I don't really think we'll ever leave it out. Actually, all the time we're going to be using this file. This is useful for us to have printing and printing functions, the printing ability, as well as reading from the keyboard. All right, so as you remember from last time, I'm going to write a main and no arguments. We're going to see arguments soon as well, actually just in a few minutes. What we want is to compute, say, the Fibonacci value of Fibonacci of 10. So I'm going to say printf, which is what you have seen last time, and the prototype for printf comes from here. You see, printf is not defined inside this file, and it comes from that header. And we're going to use exactly what we used last time. We're going to say or let's just say fib applied to 5 equals %d \n, and I'm going to put here fib 5 or 10. 10 shouldn't take too long to compute. All right, semicolon. So this would be the main program, right? We are left with defining Fibonacci of 10. What we did last time, we also used a function. The program was here, right? So what we did was we put this function at the top, right? Because the function is defined before it is being used, we did not use a prototype. This time we're going to do it in reverse, right? We're going to use it first and define it later, and that will require the use of a prototype. So I'm going to write the prototype here. I'm going to say int fib int n semicolon, right? And as the compiler reads the file from left to right and from top down, it will encounter this definition first, and it will see the use here, and it will be able to say, oh yes, it is a function that it should take an int as an argument. It does take an int as an argument, so it can perform time checking. And it is expected to return an integer, and then we are trying to print an integer here, right? So everything works out. And we can define this function below, where, guess what, we can actually even define it in a different file, right? So once we have the prototype, the compiler knows how to compile the use. It's sufficient information for the compiler to compile the use of a function, right? Obviously, the definition has to be a separate thing. So I'm going to define Fibonacci now as Fibonacci of int n, right? And notice how, right, the prototype here is this part before the semicolon is exactly this part, and that's always what it is. So if you want to take the prototype of a function, once you have the definition, you go and take everything before the opening brace and put it at the top, add a semicolon after it, and that's a prototype. It gives the compiler sufficient information to understand the use of the function, right? What type of arguments, how many arguments, what type of return result. Okay, and we're going to go with our usual definition, right? So if n is less than or equal to 1, what kind of definition do you like? The one that starts at 0 or the one that starts at 1? What are you used to? 0, right? So we can say then return n, else return f fib of n minus 1 plus fib n minus 2. All right, and semicolons should go without a space. Okay, so this is our program. All right, and let's save it. So feel free to save it under the name fib.c. I'm gonna probably be slapped on my wrist, but I'm gonna do something else. Since C is the folder that I used last time, I'm gonna move C to C old, and mkdir, I'm gonna create a new C, and I'm going to save here. Save as C indeed, and a fib.c. Right, so we've saved. Notice that as soon as it knows that the file is of type C, the language has changed here to indicate C, if depending on your IDE, right? And we get some syntax highlighting. So now we're going to do what we did last time, GCC. Let me see if it's here, CDC, sorry. ls fibc gcc minus o fib.c. Those are you who are in Windows. Instead of seeing a fib, the one that you see highlighted in red, you're going to see a fib.exe. That's normal for Windows. Executable files in Windows must have the exe suffix. If I do a list with details, so -L, which stands for long, you're going to see that this file has an X flag set here, all right, which means that it's executable. R for read, W for write, and X for executable, and it's executable by everybody, right? The owner. So the highlighted X means the owner. This means the group that the owner is in, and this means everybody else. So absolutely everybody can execute this executable. And we're going to run it, and we're going to get Fibonacci 10 being 55. And hopefully nobody has any problems with that. Is there anybody who would have a problem with that? Yes? So and you typed everything. You didn't mistype it. You're in Windows with Sigwin. Can you open a new prompt and try again? Open a new terminal. Yeah, so something is damaged with your path, probably. So sometimes there's an include among this these variables that points to the wrong place. So can you? It's still not working. So can you type this and see if you have an include there in this list? So as I type this, all right, I get this list of variables, and tell me whether there's an include. Right? Let me show it to you again. So type enter, then you can scroll up and down and see if you have an include there by any chance. An include or include there. I mean, the only recommendation without seeing it is that you may try to reboot. If you're at a point where there's nothing you would lose, and see whether that helps. If it worked before, the only thing that can be damaged is your local environment, which somehow, because of some other programs you might have run, might have had an effect on that. Yeah, and I can try to help you at the end of the class. Okay. So getting this number to be constant is boring, right? So let's try to read it from keyboard somehow, right? So we're going to learn how to use command line arguments, right? Some people nod condescendingly, which means that they know what it is about. Arg c and int star star, sorry, char. And let's do it this way. Okay, so we're deep diving here. Character, you probably figure what it means, right? It's a character. It's a small piece of memory that can hold the code for a character, not the character itself. We discussed last time that characters are sort of a abstract concept, right? We have to encode them. There are numbers associated with each of them, right? And then as those numbers are sent to the screen, there's something that turns the code into pixels without the computer actually knowing what a character is. But so there's this little piece of code that has a number in there that represents the character. And then this is a character array. And obviously a string should be a character array because there's many characters there, one after another. So it sort of makes sense to be a character array. And then this is a character array array. Means it's an array that contains arrays of characters. Now you might think this is a two-dimensional array. This is like a matrix. Not quite, because it is allowed to be jagged, right? Each internal array is a separate object and is allowed to have its own size, all right? But what we have there is an array of strings. I'm never going to say an array of characters for string. I'm always going to say string, right? So it's a character array, but we're going to say array of strings. Is this okay? Right. So what do these strings represent? Well, I'm going to write a program that is called fib, right? So I'm going to run it like this. And let's assume that fib is now a generic program. We don't really know what kind of what is computing. If I'm going to, from this current prompt, type a bunch of strings here, hi, right? Then the shell, so the shell is the program that is printing this prompt for me, right? And it is called, remember from last time? It is called what? The shell. Louder. Louder, please. Everybody says bash, bash, bash. Louder, bash, right? B-A-S-H. So very good. If you know the answer, just shout out and don't leave the others in doubt. Okay, so if I'm going to type this, bash is going to take this entire string, right? This entire string from here to here, right? And it's going to do some little processing before, right? So it's going to break this string into pieces, and the first string is going to be considered the program name, okay? And this program name, as we discussed last time, see, it kind of helps that I have the environment here, is going to be searched into this set of directories, right? And I left this one here from last time. The beauty of a Mac is that you just close it down and it stays in that same state. So I haven't rebooted since last time. It's still here. All right, so it will look for it in that list of folders. What happens with the rest? They will be broken down as separate strings and placed into an array of strings, and that array of strings gets here, comes here. Now we're going to learn soon, or relearn. So we're learning now, and we're going to reinforce it later. Arrays in C do not have an intrinsic length. All right, which adds to the danger of C. All right. So in general, the length has to be specified somehow. There's a number of ways in which that can happen. Most usually it is specified as a separate number. So how many arrays of how many elements are inside this array? The array alone will not tell us. All right. And again, a bit later we're going to understand why. We're going to talk about pointers, and we're going to understand how arrays are encoded, and we're going to understand why. But there's no intrinsic length of the array there. So the length of the array has to come from somewhere else, and this argc is that number. It's an integer. These names argc and argv have been the same for 40 years now, right? Since the beginning. So the first C program that was able to read from command line arguments, Kernighan gave these names, argument count and argument variables, and that's how everybody writes them today. So what do we really want? We want here to have, say, the integer 5, right? So we would want to read this number n. So we want to read an n from here, right? And we're going to say %d here, and we're going to print two numbers, n and fib n. Just that fib n, that n has not been defined. So I'm going to define an n, int n. As I write it like this, okay, what value do you think it has? N. Louder. Well, so is that nothing? Exactly. Exactly. So you're correct partially. It will be allocated in memory, and you are right in saying that whatever value is found there, that memory might have been used by many other programs, and there are leftovers inside that place in memory. Whatever those bits are, those bits will be considered an integer. Those sort of random bits will be considered an integer, and that will be the value of n, right? So the value of n is essentially random. That's a very general thing, adds to the danger of C. If I would write it here, nevertheless, then n will be static. We would say that n is static. N will be statically allocated. It is allocated at the point of loading the entire binary in memory. And the static area, the compiler takes care of clearing it up. It's not that it is clear, but the compiler makes an extra effort and clears it up. All right, so the n defined here will be 0. This would be called static, and by contrast, this n here is called, not really, well, it's C. So C came with its own terminology. So dynamic will not necessarily be a wrong name, right? It does reflect the nature of the n, but it's called automatic. Okay, and it's called automatic for a different reason, right? These initially the coders were supposed to use these internal variables only for variables that would be could be placed into CPU registers, right? And the compiler would bomb if you would have more variables than registers to allocate, and then they would stand for automatically allocated to registers, right? And they would call them automatic variables. Obviously, with different kinds of memory and memory being a lot faster, the decision of what to put in a register has been taken away from the coder, right? So at that time, you would say, well, the coder has to be in control of what goes into the register. Where do you need the fast computation to be, right? And whatever that is, you would put that in the register, and the rest has to be in memory. But that decision has been taken away from the coder because the compiler nowadays is much better at estimating the efficiency. So now we need to have n take the value of the first argument. All right. So I'm going to say a to I, and this A to I comes from stdio.h as well, from argv0, right? So argv0, sorry, argv1. Argv0 is, let's put argv1, let's run it, let's see that it works. And let's experiment with it, all right, and see exactly what else is there in argv. So I'm going to run this program. Just believe me for the time being that this guy here is going to be the 5. All right. If I would have another number or anything else, right, this element here will be argv2. And then later we're going to explore what argv0 is, because you're expecting that one such element exists. Okay. And then since we have an array, we're going to play a little bit with the array and see what are the dangers. All right, so let's compile. Okay, and now we can say fib 5, and we get fib. Did I save? I didn't save. Where's the 10 coming from? Okay. Okay, so I think we haven't saved properly. Something has. All right, so we're experiencing. So we have errors. All right. Again, that? Again? A to I is not from there? Implicit declaration of, we can obviously find out. That's why it's good to have an internet connection. Oh, really? stdlib. Okay, stdlib is good. So we're going to add here stdlib. I know. So I'm gonna do it this way. Okay. So star means pointer. Pointer almost means array. Almost. It's not quite. It's a bit more complicated. But just believe me that for the time being, we don't want to have much of a distinction between pointers and arrays, right? So think of everything I explained to you, and just accept that this is an array of arrays for the time being. We're going to go into more detail later, and we're going to understand everything. Okay. So what else is there? Have unmatched brackets? No, I have not saved properly. Okay, cool. So fib 5 is 5. Fib 15 is 610, and so on, right? So now we have the ability to read from the keyboard in some sort, right? There would be another way of reading from the keyboard. We're going to encounter that soon. It's probably more, you'd be more used to that from Python. You have the read in Python where the program starts running and you can type, and then you can type some input, and you might be able to type multiple lines if you want to, right? That exists too. We're going to get there. So for the time being, what happens if I don't give an argument now. What do you think? Louder. Good. So somebody has tried already. Why? So what do you think is the size of the array now? This array here. It's 1, right? It only has argv0, which is this string, right? Yet we're trying to access argv1, which would be the second element, right? So we don't own that space. That space belongs to somebody else, either a different program or the operating system, right? And we get slapped on the wrist for trying to put our hands where they don't belong. Okay. What happens if I pass in multiple numbers? So let's say I'm going to say I'm not sure 20 whether it's fast enough for 20, 20, 30, 40. What do you think is going to happen? It's very good. It's going to take only the first number that we're seeing there. The rest are going to be ignored. So indeed, this array now has 4 elements. The first element exists. We're using it. We completely ignore the rest of the elements, right? So one nice thing that we should do is to check whether we have sufficient elements before accessing the element that we need, right? And then we might want to even tell the user as a warning, hey, you're typing in too many arguments. Okay, so we can add a test. So if argc is less than 2, we can say printf insufficient. Okay, and then we can return, and this would be an error. So let's return something that is not equal to 0. And this is not Python, so we also need braces. Okay. Now, if argc is greater than 2, you can printf only one command \n, and that should be enough. And let's not forget a \n here. Okay, everybody knows what happens if I don't put the \n? Can I get what? All right, so let's experiment with that in a second, right? So let's see what happens now. All right, so compile, and now if I run without fib, we get an error message, and it no longer crashes, right? And that is very important. Whenever a program crashes, we don't know why it crashed. We don't know what's going to happen next time when it runs. So this time maybe we got lucky and it crashes. Next time maybe we lose all the data. Okay, we have to add deterministic behavior that explains very well why it happens and not allow the program to have unexplained behavior, right? So a segmentation fault is always unexplained behavior. You should not allow it to happen under no circumstance. What happens if we use more than one argument? All right, we get the warning, and in general, we should actually be a lot more explicit. We should say this is an error. We should say this is a warning. Okay, and right, so this is a warning, and we are still allowing the computation to proceed because nothing unexpected will happen. One thing we forgot to do here is to do the return 0. So you're noticing that where you don't get slapped on the wrist. Somehow the runtime will take care of that for us. But it's always good to be explicit. Let me see if I remember correctly how to do this in Bash. So this value that is being returned here, all right, we should be able to capture it. So I'm going to try to say return code equals $. I'm hoping that fib. Okay, and now I can say echo $R. Oh, this is exactly the output. I want just the one. Can't quite remember how to do that. Anyone knows how to do it in Bash? Get a return. Okay, I'll show you next time then. Get return code of command. Excellent. I'm going to find very quickly. $? All right, so if I say echo $? I would get 0 y. Oh, because the last command was echo. So let me run the fib. Okay, and then now if I run this, I'll get the 1, right? And if I have a command that runs correctly, right, as I get the return value, this will be 0, right? So the value that you see here, right, is the value that you would see here, okay? So you can now treat programs as functions, entire programs, right? This is a full program, right, running as a binary, as an executable, but nevertheless, right, it is called from the shell bash, right, and you can access the return value, right? However, the return value from a program always needs to be an error code, remember. So never think of returning the actual value of Fibonacci from there, okay? So generally return a positive number, right? 0 means no error, and from 1 onwards, right, they are error codes, and you should have some documentation on what each of the error codes means. This is the old style. Sorry, I shouldn't have written. Shouldn't have added the brackets. Is this clear so far? Are we okay? Yes? Echo is the print of bash. Do you know a different way to write it? So in C you have printf. In C you have printf. In bash you have echo, right? So for instance, in bash, just as an aside, I can say something along the lines I equals 0 while if I remember enough, $I minus LT, maybe 10 do, oh, and it's not round brackets, it's square brackets, do echo $I equals $I plus 1, done. And I didn't get to work. Let's see if this will work. $I less than 10. Oh, why did it disappear? Do $I equals $I plus 1. And actually, that's another problem. I have to write it this way. Done. Yeah, this is square again. Command not found 0 plus 1. This is square again. And the test is not working, right? But it's a language, right? So that's what you have to understand. You can write code. If you go to these coding challenge sites like LeetCode or what have you, HackerRank, right? So there's one section that says Bash, right? So there's people crazy enough to do their algorithms in Bash. Okay. Yeah. No, you can. So for the purpose of this, the behavior will not change, right? So if you want me to write this in this way, this will have exactly the same behavior, right? In general, as a principle of software engineering, right, which is another way of talking about programming, right? Software engineering is essentially industrial level programming, right? You should try to minimize the visibility of variables. They should be declared as close to their point of use as possible. You should not pollute the global namespace. This is what we say, right? Don't pollute the global namespace. You should have as few global variables as possible, right? Because every piece of code has to be as self-contained as possible. You should be able to look at a function and not need to know a lot of information from outside it to understand, right? So now if you look at the main here, you need a piece of information from outside of the function. Granted, it's very small, right? But they add up. As you keep developing and piling on code, right, it adds up. So as a general principle, yeah. Yeah. Right. So you wanna see what happens if I switch this off, right? So one way to appear to have deleted something is to comment it out, right? We haven't talked about comments yet. So you're reading from top down and left to right, right? It actually, so again, the dangerous side of C. It will actually assume that it's a function that returns an int and takes any number of arguments. All right. So in this case, actually, you're only going to get a warning. Let's see. All right. So if we go back and try to compile it, all right, you're getting a warning that fib has an implicit declaration, right? If you want to turn the warning into an error, you can take this thing from here, and this is the kind of thing that we do, right? So we take all these options of turning warnings into errors, and we put them part of the automatic build, right? So something that is not within the individual control of a coder, right? And then we block the building, and we make this kind of errors very public. So, oh, it's still a warning. Okay. Anyway, so there are ways of turning this into an error and actually blocking. Yeah. Yeah, then I don't need a prototype, right? Well, you want the choice, right?
Wouldn't that be cleaner to just
So it's more important about the fact that the file can be, that the other function can be in a separate file. Okay, maybe we should try that just for, you know. So I'm going to take this, remove it from here, okay, and have a new file. And I don't need to import anything because I'm not using any unknown functions here, right? And I'm going to save it. And I'm going to call it fiblib.c, all right? So now, no thank you. We can compile, actually it's quite easy. I can just add the other file. All right, and LD duplicate symbol for architecture. So it's not as easy as I expected. Which one is the duplicate symbol? Oh, duplicate symbol fib y. Oh, sorry. All right, if I remove this, is it possible that fib exists in one of these? No, it shouldn't, because when we, everything is saved, right? So now it works. It works properly. So why, when I add this, it doesn't? Do I need to add it here? I think I need to add it here as well. Okay. All right. So actually, it needs to be in both places, right? So and that helps. So what am I going to do now? I'm going to do since you're seeing this in both places, right? This is here as well as here. It appears twice. I'm going to actually create a separate file, and I'm going to call this fiblib.h, right? And I'm going to copy this part in here. All right. I'm going to save this as fiblib.h. Okay, and I'm going to go here and say include. And because this is not a standard library and resides in the current folder, all right, these angle brackets here say that it resides in the compilers folder, right? But if it resides in a current folder, we're just going to use quotes, right? So I'm going to say fiblib.h. And then I'm going to take this line as well, and I'm going to add it here. Control S, and then I can compile, and I can run, right? So what have we done essentially? And that's why I kind of wanted to avoid this, but since we got here, perhaps it's a good education. We have created a library. This library contains only one function, right? Each library has to come with its own header, which is this guy. The header contains the prototype. Then the prototype has to be included in all the files. So it has to be included in the library itself, here, and it has to be included in the place where it is used, which is here. Okay? So then we can compile the two files, and we obtain one executable, right? And we can run it. So in general, in large projects, you're not going to be able to stay in one file, because you can't have one file of 1 million lines, right? So you're going to write, maybe your file should be below 500 lines long, and you're going to have perhaps a few tens of thousands of files if the project is very large, right? Organized in folders and what have you. So then, how do the files know about each other, right? By building these headers, right? So you regard some of the files as libraries. You build headers containing the prototypes, all right? And then you can include the prototype, the header files in the places where those functions are used, and then compile and run. Does this make sense? So let's see if I can put them side by side. View, layout, 3 columns. Okay, so this is the library. This is the place of use. Oh, come on, I can do better than this. And this is the right. So now I have all the 3 of them. Right? So this is the library. This is, perhaps they should be like this, side by side, so that it's easy to follow. Right? So the library here, the prototype, and so the header file containing the prototype, and the main program. Right? So the main program uses this as a library and takes advantage of the function inside the library by calling it here. Cool? All right, so that hopefully answers your question. But in general, even when we have a single file, the standard way of writing that file is to put the prototypes at the top, then main, then the rest of the functions. Right? It is much more rare that you're going to see the main at the end. Right? It's also often the case that you're going to have circular dependencies because you have mutual recursion, right? So function 1 calls function 2, and function 2 calls function 1. And at that point, you necessarily need prototypes because one of the functions is going to appear before, is going to be used before being defined, right? No matter whether you put F1 first or F2 first, right? When you're going to put F1 first, F2 is going to be used before being defined. And if you're reverting them, it's going to be the same for the other function. So you need at least one prototype. But the standard is that you just write all the prototypes there. As you define new functions, you just add the prototypes, and the main comes first. Right? You sort of go in a top-down manner. Cool? Questions? With? Yes, it works with absolute paths, so you can use any path there, and you can even go not just absolute path, relative path, right? So you can go ... go one level up, and right? So whenever you use quotes means that you start from the current folder. Whenever you use angle brackets, there's a specific folder that a compiler has for header files. I can't remember where it is, but it's somewhere in libraries, I think. So if you start from the library, and it's somewhere in here, you can do a, do you have a clang? No. Is there a GCC? No. But you can actually do a search. It will take a while, and you can find them, and you can actually open them. Also, if you search this file in Google, you're going to find the source. They're quite standardized for each distribution. So GCC will have its own version, Microsoft C will have its own version, but they're pretty much standardized, and they're often assumed to be the same across multiple systems. So people rely on something being inside there, sometimes even at a specific line. They will open the file and do something with it to check whether I should write which version of the compiler is. They open an H file, and if it's this way, then it's that version. Otherwise, it's this other version. They will do things like that. Cool? Okay. Let's try to solve this problem with a while loop so that we learn what a while loop is. So this Fibonacci is recursive, all right? And since we're here, let's just change this into an iterative function, okay? Before we go there, how many times, so let's say I'm calling Fibonacci of 10. How many times this function does it get called? Do you know? How can we do that? Louder. Well, it's exponential, so that's a good estimate. All right. But it's also Fibonacci. I think it's Fibonacci of 11, right? So if I compute Fibonacci of 10, it will be called Fibonacci of 11 times. All right. Because of its recursive nature. But one thing we can do is actually find out, right? We can find out directly. So this is the beauty of actually having the computer in front of us. So I'm going to create a static variable, and it's important to be static. So we're learning now why it's static, right? Every time I call Fibonacci, as I go from this call to this call, what happens to n? Right? So I'm going to call Fibonacci, go in here, and call Fibonacci of n minus 1. So this n minus 1 takes the place of the n here. We're essentially having a new n for every call, right? Is that well understood? Okay, so this is an important principle, because recursion is possible only in this way. We're not always using recursion, but recursion is always a possibility. And just because recursion is a possibility, every time we enter a function, we're going to have a new version of this variable, right? And not only a new version of the argument, even if I put a k here, I'm going to have a new version of k as well, right? So we have a chain of calls, and inside every instance of the call, there's going to be a separate k. Whether I give it a value or not, there's going to be a separate k, right? So when I call so let's say I put this k here, even if I don't give it a value, right? I'm going to call fib5. Well, guess what? Fib5 is going to allocate some memory, and in the process of being executed, at some point it's going to call fib4, right? So that memory that is available to this guy is going to be frozen. I'm going to allocate some more memory for fib4, and then fib4 is going to call fib3, so there's going to be more memory allocated. And guess what? There's going to be 1k here, no value. We haven't given the value. We could, but right? I'm just trying to illustrate the principle. So any number of variables we'll have locally here, right? There will be a separate set of those. So there will be one k here, another k here, and another k here, right? There will be many k's. Now, if I want to count how many times this function is called, I need a single count. I need a count that doesn't get duplicated in this way. And this is why static variables are useful. Okay? So I'm going to put a count here. This count is initialized with 0, because it sits outside. Now, if you're thinking that you're going to forget, and this is a common thing, right? Because nowadays we tend to code in so many languages that we tend to forget the rules. These rules are not. There's a lot of nitty-gritty rules that are not easy to remember. So then we try to remind ourselves of what's happening and be a bit more explicit, so we can write equals 0. So we could initialize with any other value. And every time we enter the function, we can increase. So we can say count plus plus, right? Count plus plus is the same as incrementing by 1. Now you know that Python has count plus equals 1, right? And it's possible to do that in C. And this 1 can be anything else. But count plus plus is also possible, and it comes actually from the assembly language of the PDP processor. PDP, I can't even remember what it stood for, right? So it was a family of processors, not microprocessors, processors, because it was built at a point in time when microprocessors didn't exist even. Right, and you could say register plus plus to increment a register. Right, incrementing a register is a very common instruction in computer architecture, but the encoding of that for these for that assembly languages plus plus was important to see, and there we have it now in all languages. That guy who invented this notation, who was not Kernighan, must be very proud. I don't even know who he is, but you know, I mean, think of the impact. So he was designing some obscure assembly language. Maybe you also know how Unix was implemented, right? So there was a left-alone computer, forgotten computer somewhere in a corner, and Ritchie and Thompson said, "Oh well, maybe we could put this to some use." It wasn't a machine that anybody else wanted to use, right? And they had this idea of let's try to build a portable operating system, and that was their what they worked on, right? So whoever designed that machine put the plus plus in the assembly language. They, of course, were doing a lot of assembly language of that language, of that architecture to build their compiler, and then there it is nowadays, 40-something years later. Okay, so let's see how, right? So now, how do you think we get this count? Since we chose to split into files, how do you think we get this count here? Well, we have a header file, right? That's the purpose of the header file is to tell one file about the other, right? So we're going to have a prototype. Now, you might think of the prototype of being in count, right? The trouble with that is that actually, I showed you initially the shorter form that I could have used. So there's no distinction between this and this, right? For the case of the function, there's a very clear distinction because after this bracket, the closed bracket, there's a brace coming, right? So there's a very clear distinction between the syntax of the definition and the syntax of the prototype, where there are no curly braces, right? But for the variable, all right, there's no difference. So then we have to create a difference because we have to say, oh, this is actual definition and the other one is a prototype. And the way to do that is to use the word extern. Extern, if I could only type correctly. All right. So now we're essentially saying, oh, somewhere there exists an integer variable called count. And then we can actually, since we're including this here, this file will know that there is a variable called count, and we can say here, printf, the number of calls is %d count. And let's not forget about, I promised that we should experience the lack of \n. So let's delete a couple of \n's and see what happens right now, and then we're going to put them back and see the difference. So let's try to run this. Okay, so we're using the same thing, and I'm going to try to call fib20, and we're getting the number of calls is 0. Ooh. This is very strange. All right, it's at least clear what the lack of \n is doing, right? That we sort of have sorted out. So let's put the \n's back, and then let's figure out why do we have the 0. Oh, because this one is not saved. Then it's good to have to save files. I work at work with an editor that saves automatically, so I kind of lost the habit. All right, so then we have it. The number of calls is 2181 and 891. And then let's see, how much is 21? 10946 and 22. At which point? It has to be one of the. Well, I mean, it is a Fibonacci function, but it seems it's about the same as the Fibonacci function, but it seems that it's not exactly. We can come up with the number. We can try to calculate it, but it's not important right now, right? So the important thing is to see that we can actually get that number if we want to, right? And this is the technique. Yes.
So the count itself,
yes, so there's a single instance, right? It's outside of the Fibonacci, so there's a single instance of the count, and every time so the count is not on the stack, right? If you know how the compiler works, right? And I remember that you do. There's a separate area that a compiler uses. There's two areas: initialized data and non-initialized data, right? So this will be placed in the non-initialized data, which is zeroed out. Also, if I say equals 0, it will be 0 out. If you look at the compiler documentation, these would be two separate segments. One is called data, and the other one is called BSS. And I can't remember what BSS stands for, right? So the data is initialized, the BSS area is non-initialized, and it's zeroed out. If I would say something like 5 here, then the count is placed into the other area, and it is initialized with the actual value that was placed there. The difference being that this, if it's a 5, this will be saved into the binary and will take space on disk, whereas if it's a non-initialized area, it will not be saved on disk, right? It will be at runtime, the first thing that will happen is that this area is reserved and then zeroed by a piece of code, right? But there will not be a replica of that memory area on disk, right? So provided I write 0 here. Does it make sense? There's still? Yes. C, there's no such thing as immutable. I mean, you can declare a memory area nowadays immutable. I'm not sure whether you can control it from the level of C. You probably can control it from C. You should be able to actually go to the register and say immutable. Okay, very quickly, while loop. All right, and I'm going to leave the count there, and let's see the difference. All right, so how do you compute Fibonacci iteratively? There's no multiplication, only addition, right? So actually, let's not delete everything, right? If n is greater or equal than 1, return n, right? So that's still good, right? Then otherwise, we can use two numbers. Let's call them a and b, right? So I'm going to say a equals 0, int a equals 0, and b equals 1, right? And notice how we can declare multiple variables in the same declaration, and we can also initialize them, right? That actually is not so easy. And when we introduce pointers, it's going to be the difficulty is going to be revealed, right? But for the time being, we keep it simple. And so, all right. So now, while n is greater than probably 1, what do we do here? So let's add a C, which we don't need to initialize, and we're going to say C equals A plus B, B equals A, C equals B, B equals A plus B, and A equals C. Right, something like this, and then we should return C, I think. Sorry, C or B? Then B. Okay, so if n is 2, then we execute once and we return B, which is the right value. And n has to go down by 1. All right. And this should work, right? And now, obviously, number of calls is just 1. Right? It's the same value. I'm hoping, yes. Okay, cool. So with the knowledge of other programming languages that you have, is this sufficiently easy to understand? Yeah. Any problems? So one thing that is very different from, say, Python is the curly braces, right? We don't use indentation to show blocks of code, right? We use these curly braces. I'm using a notation that is sort of trying to save space a little bit, where the curly brace, the open curly brace is on the same line. There are styles of C that will go like this, right? In general, because of the curly braces, you can mix and match the style. So this will be correct code, right? Obviously not recommended. I can put it here, correct code, right? Try to keep everything neat and nice and tidy. Okay. So very quickly, let's experience another kind of loop, which is the for loop. It's probably a bit more common, right? So I'm going to add a counter, and the counter can be defined inside the for loop. So I'm going to say for int I equals 0, I less than probably n minus 2, I plus plus. Right. So this is in a way easier to use because it doesn't let you forget the I plus plus. Okay. But these are just instructions, right? So this is executed at the beginning. This is executed. This is also executed every time at the top of the loop, and this is executed all the time at the bottom of the loop, right? So you can think of here right before c equals b, we're going to perform this test, right? And right here, right after the n minus minus, which you actually don't need anymore, we're going to perform the I plus plus, right? So we're going to do this n minus 2 times. Let's make sure that it works correctly. If n is equal to 2, then we don't execute this at all. So probably this needs to be n minus 1. So if n is equal to 2, this gets executed once, and it's probably the correct thing. Okay, so there's not much difference between while and for. In some languages, there is a clear difference because you're not saying the I plus plus. The I plus plus is implicit. In C, it isn't. Right? Almost all computations can be expressed that use of for can be expressed with while and vice versa. Any of these parts can be missing, right? So I mean, this will, in this case, will not be a correct program, but it will be syntactically correct. It will be syntactically correct to not have anything here. Okay, and the result of that is that that stands for empty. So nothing is executed at the top of the loop. Right, nothing is executed as a test, so you can have an infinite loop if you want, and nothing is executed after each iteration. So, for instance, something like this, for and do something, is actually quite common in programs, right? So this is do something infinitely. It's an infinite loop. It's a very common way of saying infinite loop. Okay, so this is our program. Let's compile. Let's run. It works. And this is the for loop. Cool? All fine? Questions? Still awake, that's good, given the lack of light. Cool. This is the class for today. Thanks for coming. See you next time.